Salient-Pole Synchronous motor. The armature of Salient-Pole motor is similar to that of the cylindrical rotor motor. However, due to the silency, the air gap is not uniform and the flux is dependent on the position of the rotor. The field winding is normally wound on the pole pieces. The armature current and the reactance can be resolved into direct quadrature axis components, that is ID and IQ. ID and IQ are the components of armature current in the direct axis and quadrature axis respectively. Now similarly, XD, XQ are the direct axis reactance and the quadrature axis reactance respectively. Now from the equation number 1, the voltage will become Vf equals to Va minus J XD ID minus J XQ IQ minus Ra Ia. For negligible armature resistance, the phasor diagram is shown here. Then from the phasor diagram, the ID is given by Ia sine theta m minus delta. This is delta and this is theta m. That is equation number 14. Then IQ is equals to Ia cos theta m minus delta. Let it be 15. Now ID XD equals to Va cos delta minus Vf, let it be 16. Now IQ XQ equals to Va sine delta, let it be 17. Now substituting the value of IQ from the equation number 15 into 17, we are going to get Va sine delta equals to XQ Ia cos theta m minus delta, that equals to XQ IQ cos delta cos theta m plus sine delta sine theta m. Let it be equation number 18. Now dividing both the sides by cos theta and solving for delta, we are going to get delta equals to minus tan inverse of Ia XQ cos theta m divided by Va minus Ia XQ sine theta m. Let it be equation number 19, where the negative sign signifies that Vf lags Va. If the terminal voltage is resolved into D axis and Q axis, that VAD is equals to minus Va sine delta and VAQ equals to Va cos delta. Now the input power will become P equals to minus 3 ID VAD plus IQ VAQ, that equals to 3 ID Va sine delta minus 3 IQ Va cos delta. Let it be equation number 20. Now substituting the values of ID and IQ from equation number 16 and 17 respectively, now the PD equals to minus 3 Va Vf divided by XD sine delta minus 3 Va square by 2 XD minus XQ divided by XD XQ sine 2 delta. Let it be 21. Now dividing the above equation by the speed gives the developed torque TD equals to minus 3 Va Vf by XD omega s sine delta minus 3 Va square by 2 omega s XT minus XQ divided by XT XQ sine 2 delta. Let it be equation number 22. The torque has two components. The first component is same as that of the cylindrical rotor if XD is replaced with XS, and the second component is due to rotor silency. The typical plot of developed torque against the torque angle delta is shown here, where the torque has the maximum value at delta equals to plus or minus delta m. For stability, the torque angle is limited in between minus delta m less than or equal to delta less than or equal to delta m, in between these two. And in this stable region, the slope of TD delta characteristics is higher than that of the cylindrical rotor motor. This is regarding the Salient-Pole synchronous motors. Reluctance synchronous motor. The reluctance motors are similar to the Salient-Pole motors except that there is no field winding on the rotor. The armature circuit, which provides rotating magnetic field in the air gap, induces a field in the rotor that has a tendency to align with the armature field. The reluctance motor are very simple and are used in applications where a number of motors are required to rotate in synchronism. These motors have low lagging power factor, typically in the range from 0.65 to 0.75. With Vf equals to 0, the equation number 22 can be applied to determine the reluctance torque, that is given by Td equals to minus 3 Va square divided by 2 omega s xd minus xq divided by xd xq sine 2 delta, let it be 23, where delta is equals to minus tan inverse of Ia q cos theta m divided by Va minus Ia xq sine theta m, let it be 24. The pull-out torque for delta equals to 45 degrees will be maximum, that is Tp equals to 3 Va square divided by 2 omega s xd minus xq divided by xd xq, let it be 25. Next one, fourth, permanent magnet synchronous motor. The permanent magnet motors are similar to Salient-Pole motors except that there is no field winding on the rotor and the field is provided by mounting the permanent magnet at the rotor. The excitation voltage cannot be varied for the same frame size. Permanent magnet motors have higher pull-out torque. The equation for the Salient-Pole motors may be applied to permanent magnet motors if the excitation voltage Vf is assumed to be constant. The elimination of field coil, DC supply and slip ring reduces the motor losses and complexity. These motors are also known as brushless motors. And finding increased applications in the robots and mechanic tools, a permanent magnet motor can be fed by either rectangular current or sinusoidal current. The rectangular current fed motors, which have concentrated winding on the stator inducing a square or trapezoidal voltage, are normally used in low power drives. The sinusoidal current fed motors, which have distributed winding on the stator, provides a smoother torque and are normally used in high power drives. This is regarding reluctance synchronous motor and permanent magnet synchronous motors. Fifth one, switched reluctance synchronous motor. A switched reluctance motor, that is SRM, is a variable reluctance step motor. This is cross-sectional view, and this is having 3 phase Q equals to 3 with 6 stator teeth, Ns equals to 6, and 4 rotor feet, Nr equals to 4. Nr is related to Ns and Q by Ns plus or minus Nr by Q. Each phase winding is placed on 2 diametrically opposite teeth. If phase A excited by a current Ia, a torque is developed and it causes a pair of rotor poles to be magnetically aligned with the poles of phase A. If the subsequent phase B and phase C were excited in sequence, a further rotation will take place. The motor speed can be varied by exciting in sequence phases A, B, and CA, commonly used circuits to drive an SRM as shown here in the drive circuit. An absolute position sensor is usually required to directly control the angle of stator excitation with respect to the rotor position. A position feedback control is provided in generating the gating signals. If the switching takes place at a fixed rotor position relative to the rotor poles, an SRM would exhibit the characteristics of a DC series motor. By varying the rotor position, a range of operating characteristics can be obtained. This is regarding the switched reluctance motor. If this video is useful, please like, share and subscribe.